All right, so we're going to use our time derivative equation here of ds dt. We're going to show how this particular particle that follows this sort of path, what is the velocity of this particle, what is the equation of the velocity, and then what is the acceleration equation. So with a particle that follows this path, y is equal to x minus x squared divided by 200. It's going to follow a path similar to that, baseball, football, whatever the case may be. We're going to say that its velocity in the x direction is 40 times 2 square root meters per second, feet per second, whatever you decide is fine. All right, so let's see. Well, first thing we got to do. The first thing we need to do is take the time derivative of y. And since this is a composite function and this is in the function, it's in x, we're going to have to use the chain rule. And exactly how we do that is dy dt is going to be equal to dy dx dx dt. So once we use the chain rule to find out what dy dt is in this particular equation, we see that dx dt is right here, and dy dx is simply, we're going to have to take the derivative of this thing. So let's do that. So let's go dy dt is going to be equal to the derivative of this thing, which is going to be dy dx, which is going to be 1 minus x divided by 100. And we're going to be multiplying this by 440 times 2 square root. So this is our dy dt, which is going to go right in here. So now we know dx dt, which is this, and we know dy dt. So we know dx dt, we know dy dt. So we got these two. Very important. And our dx dt is over here. So let's see. Let's plug this thing into this equation and see if we get. So we have ds dt is going to be equal to 40 times 2 square root, and we're going to square that, and we're going to square this side, and then plus 1 minus x divided by 100. We're going to square that, and then we're going to say 40 times 2 square root, and we're going to square that. So this is this thing right here. So we put our equations into this, and let's see what we can get. All right, so we can factor out the 40 times 2 square root. So we can do that. So ds dt squared is equal to 3200, because that's basically what this is. We factor that out, we're going to get 1 plus 1 minus x divided by 100 times 1 minus x divided by 100. So basically we squared this thing and we pulled this out. All right, let's keep on going with the algebra. So what we want to do is multiply this thing out. So ds dt squared is going to be equal to 3200. So we're going to have 1 plus 1 minus 2x divided by 100 plus x squared divided by 10,000. All right, well, 2 divided by 100 is just 1 over 50, so we can get rid of that. And we can come up with ds dt squared is going to be equal to 3200 times 1 plus 1 is 2 minus 1 over 50, or x over 50 rather, x over 50 plus x squared divided by 10,000. All right, so we need to get rid of this 10,000 because we got the x's to be the alone. So we're going to factor out a 10,000. When we factor out a 10,000, we're going to get a ds dt squared is equal to 3,200 divided by 10,000, and that's going to be equal to 20,000 minus 200x plus x squared. And when we take this number and we get rid of some of these zeros, we're going to get 32 over 100, which is basically 8 divided by 25. So we get ds dt equals the square root of 8 divided by 25 times x squared minus 200x plus 20,000. And this is our equation for the velocity in this particular problem. Now, in order to find the acceleration, we got to take the derivative of this thing. I don't like taking derivatives of the square root, so we're just going to bring the square back over, and we're going to have ds dt squared is going to be equal to our 8 divided by 25 x squared. Can I use x squared? Yeah, sure, why not? X squared minus 200x plus 20,000. And we're going to take the dt of both sides. So when we do the dt again, now look, this is a derivative, this is a differential equation. So when you have a differential equation in here, when you take the derivative of this thing, you're going to have to take the 2 and bring it down here, and then you're going to have to take a derivative of this thing inside. So what you're going to get is 2 ds dt, right? What's the derivative of the thing inside? Is the second derivative of ds dt. And what is the second derivative of ds dt? This is acceleration, and this is exactly what we're going to look for. So this is going to be equal to the derivative of this, which is going to end up being 8 divided by 25 times 2x minus 200. Now be very careful here. That's not just the derivative. We also got an x in here. We got it because we're taking the dt of this thing. This is the derivative of the time. We've got to put in a dx dt in here because it's a composite function. So now, what is our dx dt? It's up here. So we plug that in. So we got 2. We know what ds dt over here, so we can put that in as well. So we have, it's going to be not much room here, but I'll try it and see if I can bring that 2 over a little bit more. Bring a line over here. Bring this 2 here. I'll try to squeeze this all in, which would be 8 divided by 25 times x squared minus 200 x plus 20,000 2, 3 square root this whole thing times our accelerations, which is d squared s dt squared, and then this is going to be equal to our dt, so this is going to be 8 divided by 25 times 40 times 2 square root, so, and then 2x minus 200. We're almost home. What do we have to do? Divide both sides by this, so we get d squared s divided by dt squared is going to be equal to, let's do some, let's just go ahead. Let's go ahead and do this. 40, 2 times square root, divided by 25 times 2x minus 200. We're going to divide this whole thing by 2. 8 divided by 25, x squared minus 200, x plus 20,000, square root. Once we do all the algebra inside here. I'm not going to go through all that, but once you do all the algebra in there, this becomes ds dt squared. It comes out to be a nice little number, which is basically 32. We pulled out a 2 out of here, so this is 32 times x minus 100, because we pull that 2 out, and we get an x squared on the bottom, minus 200x plus 20,000 square root. And this is our acceleration equation for this particular problem. So we found velocity, we took the derivative of that, we found acceleration, and that is how you use this incredibly beautiful equation. I hope that helps you. Please let me know, and I hope that next time it can have a better one. See ya, thank you, and describe.